This is AQA GCSE. It's a separate science chemistry topic. It's at the end of the bonding chapter and we're introducing the concept of nanoparticles. But if you're doing dual award, you do not need to cover this content. I'm going to recommend that you pause on the activities and have a go at them, then you get to see how you're progressing. So, in this video, we are going to look at the comparison of nanodimensions to typical dimensions of atoms and molecules. And we've been given some information here. One nanometer is 1 by 10 to the minus 9 meters, or 1 billionth of a meter. And there's a question here to try to break down. How do nanoparticles compare in size to normal-sized particles? Which of these would you think is the most logical answer to that question? Well, the first thing to consider is we can't just talk about being small. We have to get across that they are very small. The scale of difference in size has got to be there as part of your answer. So we can get rid of the middle two. The final part is just a little bit of exam technique. We're being asked to compare to normal-sized particles. So we can't just say they are very small. They are very small, and that is a description we could give in another context, but it's a comparison, so we must say they are much smaller. Okay, have a go at converting these. So we know that there are 1 by 10 to the power of 9 nanometers in a meter. So we're going to multiply all of these by 1 by 10 to the power of 9. So first one, 100 times 1 by 10 to the 9 is 1 by 10 to the 11 nanometers. On the next one, going through these a bit quicker, that's going to come to 100 nanometers. The next one, 0.1 nanometers. And the next one, 1 by 10 to the minus 4 nanometers. We're next going to move on to consider surface area to volume ratio. If we have a higher surface area to volume ratio, we have got more of the substance exposed at any one time. And that becomes really important when we consider rates of reaction and surface area in a later topic. So we're told here that nanoparticles are generally between 1 and 100 nanometers. What would they be in meters? Well, we've just done this in reverse. So we're going to divide by 1 by 10 to the power of 9 in this case. So I'm going to colour code them. 1 is going to be 1 by 10 to the negative 9 meters, and 100 will be 1 by 10 to the negative 7 meters. And then we've got some calculations to do on surface area to volume ratio. Going to recommend that you pause and read through this and then have a go at the questions that follow. So, a couple of questions for you to try here. And we're breaking it down into calculating surface area, then volume, and then surface area to volume ratio. So for a 500 by 500 by 500 centimetre cube, the surface area, each side of the cube is 500 by 500, and there are 6 of those surfaces. So that comes to 1.5 million centimetres squared. But the volume is going to be 500 by 500 by 500, which is 125 million centimetres cubed. Now my surface area to volume ratio is therefore 1.5 million to 125 million. And when I work out that ratio, it comes to a value of 0.012. If I do the same thing with a much smaller cube, 50 by 50 by 50, I get a surface area of 15,000 centimetres squared, and I get a volume of 125,000 centimetres cubed. So my surface area to volume ratio here is 15,000 to 125,000, which gives me 0.12. So as the cubes have got smaller, we're exposing more surface area, so the surface area to volume ratio increases. Let's have a go at an even smaller cube now. So 5 by 5 by 5. Well, my surface area is 150 and my volume is 125. So my surface area to volume ratio is 1.2. So we've gone up again, and that's going to mean a faster rate of reaction when you're thinking about this in the rate of reaction topic. And even smaller again, going down by a factor of 10, 0.5 times 0.5 times 6, we have a surface area of 1.5 centimetre cubed, and we have a volume of 0.125 centimetres cubed. Now, if I do my ratio, 1.5 to 0.125, I get a surface area to volume ratio of 12. So again, the important thing to take from this is that as we break something down into smaller particles, if I break that sample down into smaller cubes, I'm exposing more surface area, so the surface area to volume ratio increases. Now, when we're doing this with nanoparticles, we are hugely increasing the surface area to volume ratio, which we can then think about the incredible impact that that's going to have on absorption and rate of reaction. That takes us to the end of this video. Thank you for listening and goodbye.